We used to joke that triangulation was the most boring thing in astronomy. Measure the same object from different places, solve a bit of geometry, get one clean answer. No drama. Orbital mechanics is supposed to be the part of the universe that behaves. It took 3I/ATLAS exactly 3 nights to ruin that belief. When NASA asked us to launch Keck, the VLT, and Subaru in a single, synchronized mission, it almost felt like a demonstration experiment. 3 flagship ground-based observatories, 3 planetary summits, 1 interstellar object, which had already been described as strangely out of step with conventional models. By this point, Atlas had already managed to surprise us with its spectrum, green glow, and hyperbolic orbit, but at least it had flown fairly so far, within the margins of error, within the limits of physics. The campaign's main objective was simple and straightforward: to obtain the most accurate parallax and velocity for 3 I/ATLAS in order to adapt the dynamical model to all new observations. Keck in Hawaii, the VLT in Chile, and Subaru on Mauna Kea were to observe the comet simultaneously according to a coordinated schedule with strict synchronization in time and stellar references. We rehearsed this scheme using standard objects, nearby asteroids, Jupiter's moons, and several calibration galaxies. Everything matched to the milliarc second. No surprises. On the first night, frankly, no one expected miracles. We were simply delighted with the idea itself. An interstellar visitor, 3 telescopes, a ton of fresh data for papers and grants. I sat in the darkened processing center hall in front of a wall of monitors where telemetry and rough images streamed in real time. On each screen, a familiar glowing dot framed by star fields. 3I/ATLAS looked the same everywhere. A faint, slightly elongated profile, the tiniest hint of a tail. The first rough centroid measurements showed what we expected: a slight parallax between the observatories, a few pixel offset easily converted to distance and angular velocity. I noted in the log, everything is textbook. We ran the standard pipeline: correction for optical distortion, atmospheric dispersion, alignment with Gaia stars, and error estimation. Then the 3 teams sent their position catalogs to a shared server, where the tedious finale awaited them, one beautiful trajectory with small confidence ellipses. Only the confidence ellipses did not overlap. At first it looked like a trivial glitch. On the combined diagram, the points from Keck, VLT, and Subaru formed a thin triangle, not a tight cluster. 3 clusters, each neat in its own right, with low internal dispersion, but shifted relative to the other 2 by amounts that couldn't be attributed to turbulence, clock drift, or calibration errors. Not tenths of a milliarc second, but full tens of milliarc seconds. For an interstellar comet at that distance, this meant kilometers, if not tens of kilometers, of difference in position. Astronomers can be paranoid, of course. For the first few hours, all we did was look for someone to blame. We checked the time synchronization. All 3 observatories were connected to the same atomic reference via GPS and fiber optics. We checked the star catalogs, Gaia EDR3, the same identifiers, the same coordinate system. We checked the atmosphere, water vapor, seeing, temperature, everything was normal. Just to be sure, we ran the same frames through alternative software and other centroid determination algorithms. Nothing changed. 3 independent functioning telescopes confidently showed 3 slightly different positions of the same object. I remember someone in the room trying to joke, "Well, in quantum mechanics, an object can be in multiple states at once. Maybe Atlas is just big." The laughter quickly died down when we plotted the orbits separately for each dataset. For Keck, the comet followed a single, pure hyperbola, slightly steeper than the previous night's data. For the VLT, it followed another, slightly offset, with a minimally different escape velocity. For Subaru, it followed a third, even closer to the escape velocity limit. All 3 orbits were internally consistent, yielded good chi-squared, described their respective sets of points perfectly, and categorically refused to coalesce into one. Attempts to find a single trajectory that would at least absorb all 3 sets within reasonable error failed. The model either drifted off into parameter madness or produced a monstrous residue. This doesn't happen in classical astrometry. If the instruments are reliable and the calibrations are accurate, then the starry sky is the same sky for everyone. The second night, we went out with the mood of forensic experts. NASA insisted on repeating the experiment with a more rigorous protocol. We increased the frame rate, added parallel observations of control objects, and expanded the list of standard stars for verification. Every few minutes, we paused Atlas imaging, reset the telescopes to calibration fields, and verified everything from zero. This time, the verification pipeline took longer than the observations themselves. The result was worse than the first time. On the control objects, everything was perfect. Asteroids, satellites, galaxies, everything matched down to the last pixel. but as soon as we switched to 3I/ATLAS, the situation repeated itself. 3 neat but incompatible sets of coordinates, 3 mini-universes, each with a comet following its own trajectory. If we plotted everything in a single graph, it appeared that Atlas was spread across 3 closely spaced orbits, as if its position were not a point but a thin, 3-lobed figure in phase space. NASA's internal chat filled with graphs, screenshots of diagrams, and those same short phrases people use to hide panic behind professional dryness. It doesn't fit the model. There's no physical parameter that would produce such a pattern. If it's systematic, why is it only perfect on Atlas? On the third night, we brought in another check, an independent group who had no idea what object they were calibrating. They were simply given a set of anonymous images from 3 telescopes and asked to plot the trajectory of object X. They arrived at the same 3 orbits, unaware that they should have one. Somewhere after this, the word systematic error became obscene. The first informal discussions of the hypotheses began in a small room, unofficially, without the press, and off the record. People from JPL, observatory coordinators, a few theorists, and a couple of quantum gravity specialists, invited almost as a joke, were present. 3 colored lines hung on a projector, red, blue, and green, representing the 3 Atlas orbits that were clashing. Someone suggested exotic refraction in interplanetary plasma. Someone else suggested a hidden satellite, ATLAS, which produces different projections. Someone else tried to pin it all on local gravitational disturbances, as if an invisible body were passing nearby. Each proposal fell apart against simple facts. Other objects in the same field of view would suffer, at least slightly, but only the comet suffered. It was then that a phrase was uttered that had long been avoided in official documents. What if we really do see different phase configurations of the same object? This was said by a theorist who had spent his entire life pursuing what normal astronomers considered almost philosophical: the many worlds interpretation, macroscopic coherence, phase space with branching trajectories. Until that moment, his presence at the meeting seemed a polite tribute to the fashion for quantum exotica. After this statement, the room became as quiet as if someone had turned off the air conditioners. The idea was crazy and at the same time frighteningly neat. Imagine an object not as a single point on a single trajectory, but as a distribution across several closely spaced trajectories. In everyday life, this multidimensional structure is reduced to a single realization: observation, interaction, decoherence, and that's it. We get the classical result. But if for some reason this object maintains macroscopic coherence longer than it should, different observers with different instrument configurations can project different slices of this structure onto themselves. Each telescope sees its own layer of Atlas, its own realization of its position and velocity. On a quantum scale, this is commonplace: an electron in 2 slits, a photon that behaves like a wave until you look. But on the scale of an interstellar comet, hundreds of meters, thousands of tons of matter, it seemed almost blasphemous. The problem was that the data behaved as if that was exactly what was happening. We set up a 4th night of observing, this time with the addition of another site, a less powerful observatory, but still quite sensitive. A medium-sized telescope in the northern hemisphere was added to the 3 giants to check if a 4th orbit would appear. We configured everything so that the observations would proceed almost simultaneously, with minimal delays. It appeared, not as displaced as the 3 main ones, but still discernible. The 4th set of points lay slightly off to the side, demanding its own 4th hyperbola. Somewhere around this point, it became clear we'd gone beyond the usual emergency scenarios. It wasn't a calibration error, a software bug, or a detector nonlinearity. We could recheck the hardware and software as much as we wanted. Everything worked perfectly. Something else was failing: the very premise that there's only one single 3I/ATLAS position at any given time. Officially, NASA still called it anomalous divergence in astrometric estimates. Other words were bandied about in emails and private channels: branched phase, multi-configurational object, macroscopic branching. No one wanted to mention the word quantum near the comet, but it hung in the air like the scent of ozone before a thunderstorm. We decided to conduct an experiment that would have seemed absurd in a normal situation. If each telescope, roughly speaking, sees its own version of Atlas, what happens if we change the observation itself? Not the camera mode or the exposure, but the fundamental structure of the campaign. We divided the following night into a series of windows. Some involved all 4 telescopes at once. Others involved only 2. Others involved only 1, while the others looked at other parts of the sky. The result wasn't just strange, it was structured. In windows where all 4 observatories were active, we again saw 4 stable but incompatible orbits. In 2 out of 4 windows, the number of stable solutions was reduced to 2, with the set of orbits changing depending on which telescopes were participating. If only Keck and the VLT were active, the red and blue trajectories survived. If Subaru and the middle telescope remained, the green and the new 4th trajectory prevailed. Most alarming were the intervals where Atlas was observed by only 1 observatory. In these blocks, the data seemed to become perfect. A single, clean, perfectly fitting orbit, minimal scatter, a fantastically beautiful chi-squared. But when we tried to combine these single solutions, they again disagreed. It was as if each telescope, left alone with the comet, had its own world, its own uniquely correct atlas, until we tried to combine these worlds into a single picture. The word dimension suddenly ceased to be innocent. It felt as if the very attempt to observe 3I/ATLAS simultaneously from different points was forcing it to spread across multiple branches of reality, with our data summary merely highlighting the dissection lines. This certainly sounded like metaphysics, but the mathematics stubbornly followed suit. Not everyone agreed with this interpretation. Within NASA and JPL, a fierce opposition to any quantum romance arose. People who had spent their entire lives working with trajectories, engines, and landings rebelled against the idea that their world of meters and seconds had suddenly transformed into a canvas of probabilities. They sought more mundane explanations: unknown gravitational lenses, plasma jets, extended tails with non-uniform density, massive ejections from the core. We honestly tested every hypothesis, adding ever new parameters to the models. The more parameters we added, the more obvious it became that we were simply bending reality to our own fear of admitting it was different. At one point, the theorist, the very one who first uttered the term phase configurations, quietly remarked, "Have you noticed that all your classical models require invisible structures that behave as if the object were distributed across several states? You've already constructed a quantum interpretation. You're just afraid to call it that." The most frightening thing, perhaps, was not the behavior of ATLAS itself, but what began to happen around it. A couple of weeks into the synchronous campaign, several independent teams working on completely different tasks, tracking close-passing asteroids, refining satellite orbits, began complaining about minor discrepancies. Nothing dramatic. Centimeters, meters, micro arcseconds, but all these discrepancies were related to objects observed on nights when their field of view intersected with the 3I/ATLAS trajectory. It looked like a faint shadow of the same effect we saw on a larger scale. Small but consistent differences in position estimates, depending on who was looking and when. One of our colleagues, a specialist in near-Earth space mechanics, sent me a private message. "I don't know what you're doing with your comet, but I have 3 different orbital solutions for the same piece of junk, and each solution matches perfectly with data from a single tracking station. When I put them together, I get the same damn triple configuration. And this isn't some exotic interstellar object anymore. It's a piece of an old rocket panel." It was then that a term appeared for the first time, which they then tried to erase from official correspondence for a long time: phase infection. The idea was simple and terrible. If 3I/ATLAS truly is an object that exists in multiple macroscopic configurations, then every interaction with it, every photon, every radio wave, every gravitational whisper bears the imprint of this multi-configuration. Our telescopes, sensors, and tuning algorithms begin to involuntarily adapt to this logic, rewriting their internal standards as if multi-configuration were the norm. And then it no longer matters whether we're looking at Atlas or a piece of space debris. The measurement system itself becomes branching. It was, of course, a hypothesis bordering on science fiction. But like any good horror story, it perfectly explained too much at once. The culmination came on the night we attempted to use the same observation infrastructure to solve 2 problems simultaneously. Continue the 3I/ATLAS campaign and conduct critical measurements for the next asteroid rendezvous mission. We couldn't afford to make a mistake. Launch windows, fuel consumption, and the entire mission architecture depended on trajectory accuracy. The data on the asteroid came back strange. At first glance, everything seemed fine. But when the orbital dynamics team began constructing a solution, their graphs looked suspiciously like our Atlas diagrams. 3 adjacent perfect solutions, each perfectly fitting some of the data, but categorically refusing to accommodate the rest. I've since replayed the recording of that meeting many times. People accustomed to dry numbers sat silently, staring at screens where the world was disintegrating into branches. At one point, one of the engineers, a man without a penchant for pathos, said, "If we choose one solution and it turns out the world preferred another, we'll miss the asteroid by tens of kilometers. And if we make a mistake with Atlas, no one knows yet how it will end." 2 days after this meeting, a closed circular arrived. The text was carefully scrutinized to the point of sterility. Due to the need to minimize uncertainties in critical trajectory estimates, all further observations of the 3I/ATLAS object as part of synchronized campaigns using several large observatories are temporarily suspended. It is recommended that monitoring be limited to single observation channels with subsequent independent data processing. Between the lines, another message read, "Stop looking at him at the same time. We're not sure the world can withstand another round." Keck, VLT, and Subaru formally continued their work, but they no longer converged on the same target at the same time. Each took their own photographs, their own estimates, their own ideal orbits. A flood of articles appeared in the open literature on Atlas, with each team confidently plotting its own trajectory and conclusions. Official reviews cautiously noted discrepancies in estimates requiring further analysis. They tried to avoid using the word phase. Sometimes I'd open the internal archive and look back at those first nights, when we still believed 3 telescopes would give us a single, beautiful line. At the initial frames, where Atlas was still just a faint dot against the background of stars. At the graphs, where the red, blue, and green orbits were beginning to diverge, like roads at a fork in the road beyond which there's no turning back. There are moments when you acutely feel like you've done something that you shouldn't have. Not because it's forbidden or dangerous in the conventional sense, but because it's altered your very relationship with reality. When we first decided to simultaneously look at 3I/ATLAS through the planet's 3 eyes, we simply wanted to clarify its path. Things turned out differently. For the first time, we forced the universe to demonstrate that there might be more than one path, that a trajectory isn't a line on a map, but a spectrum of possibilities that, up to a certain point, exist side by side, without interfering with one another, and that sometimes it is enough to just look too closely from 3 places at once for this fan to stop hiding. Since then, I've taken a different look at all the neat curves we use to describe the motion of celestial bodies. I look at every trajectory confidently drawn in a report and sold to the public as an object's path. We're used to thinking that collecting more data is enough to narrow the margin of error, but the experience with 3I/ATLAS has shown something different. Sometimes the data itself expands the world in which it exists. ATLAS continues to drift away. Each telescope sees its own velocity, its own hyperbola, its own story of separation. Officially, we say the discrepancies decrease as the object moves away and the measurement accuracy decreases. Unofficially, some of us whisper to each other that we've simply stopped integrating all the data into a single model. Sometimes it's easier not to try to put the world together. Sometimes it saves you to look at space from one place, with the same eyes, in one version of reality. And somewhere out there, on the edge of the solar system, a comet from an alien star region continues to fly along several orbits simultaneously, and perhaps each of them tells its own story of what happened when 3 Earth-based telescopes attempted to simultaneously observe the same universe for the first time. My first instinct was, of course, to blame everything on earthly problems. The atmosphere, optics, software, people. When 3 observatories, separated by thousands of kilometers, simultaneously observe the same tiny interstellar object, you expect a scattering of results, but not this. Not 3 consistent solutions, each perfectly consistent within its own coordinate system and categorically incompatible with the other 2. Keck swore by his mirrors that Atlas was slightly closer to the calculated trajectory and moving a fraction of a second faster. The VLT projected the comet's declination higher and with a barely noticeable lateral shift. Subaru presented its third version, with the tail slightly tweaked, and the nucleus shifted a few milliseconds laterally. Individually, all 3 sets looked flawless. Calibrations, atmospheric corrections, standard comparison stars, everything matched down to the last digit. But when attempting to assemble a unified 3-dimensional solution, the space literally burst at the seams. Someone in the dynamics department quietly joked that we'd captured the first macroscopic analog of quantum superposition. Atlas is here and there again, until we force it to define itself. The joke caught on, and by the next day was making the rounds in internal chats as memes. Don't look at Atlas until you know what configuration you want it in. This gentle irony concealed a very inconvenient truth. No one could point to a specific error. All 3 versions of the comet behaved like physically real trajectories. NASA launched a process we later called the reconciliation campaign. The Keck, VLT, and Subaru teams re-examined everything from the mount mechanics to the image reconstruction algorithms. They added independent control fields, observed familiar asteroids, Jupiter's moons, even satellites, and achieved a perfect match everywhere. Only when 3i/ATLAS appeared in the frame did reality begin to behave like a poorly stitched photo collage. The turning point came when one of the analysts working with the raw data decided to visualize not only the nucleus's position, but also the entire region of likelihood for each telescope. This appeared as 3 translucent ellipsoids floating in a volume around the calculated trajectory. In a normal world, these clouds should overlap, forming a zone of maximum confidence. In ours, they almost touched each other, like 3 soap bubbles suspended in one spot, but refusing to merge. He started a time-lapse animation, and we all fell silent. As the Earth rotated and the observatories faded into day, returned to night, and picked up Atlas again, the clouds didn't just tremble, they described a delicate, almost ritualistic dance around each other. None of them overlapped. The trajectories were parallel, close, like railroad tracks, but they didn't intersect or merge. It was as if each telescope had its own, slightly shifted version of the event, and our shared world stubbornly refused to choose one. A hypothesis was born within NASA, officially known as the multi-configurational phase structure of the object. Unofficially, it was called something simpler. Atlas exists in several phase variants, and each telescope sees a different comet. Admitting this would have meant putting one foot outside the bounds of what's acceptable in classical astronomy. So, at first, they tried to make the hypothesis look respectable. Someone proposed a model of a complex multi-layered coma, where different layers of gas and dust interact with the solar wind in such a way that different wavelengths supposedly see different effective brightness centers. This version was convenient, understandable, and consistent with physics. They even tried to push it into the first draft of the press release. The unique structure of the coma, a rare case, was supposedly a perfect opportunity for grants. But the problem was that the discrepancy wasn't just in brightness. The calculations neatly revealed differences in velocity and even in the radial component of motion. If it were just a matter of the photometric center fluctuating, we would have long since closed the matter. But the numbers persistently hinted. There are 3 slightly different ATLAS, each with its own orbit, and our instruments are accurately recording precisely that. One evening at a closed call, when we were again at an impasse, a theorist from JPL said out loud what everyone had been avoiding. What if the problem is not in the object, but in the observers? The silence that followed was thicker than any vacuum of space. He continued, calmly, almost casually, as if he were discussing meteorology. We have 3 instruments, 3 independent processing chains, 3 different frames of reality tied to 3 points on a rotating planet. We believe they are all embedded in the same physical continuum. But what if Atlas is the first object at whose scale the differences between how each frame fits into this continuum become noticeable? Official science dislikes the words multiverse, branching, and decoherence. These terms live in articles on the interpretation of quantum mechanics far removed from observational work. But we've all secretly read these texts, and what he said sent an inexplicable chill down our spines. If Atlas carries some internal phase structure sensitive to observing conditions, he continued, we can see not just one object, but a cross-section of a whole fan of possible trajectories, and each telescope, tightly bound to its location and history, presses one of these branches. It sounded like a pseudoscientific thriller. But the more we twiddled the data, the fewer internal contradictions we found in this absurd, terrifying model. In an attempt to test it, NASA sanctioned an experiment that would normally be frowned upon. They decided to perform a sort of forced collapse on a macroscopic object. All available major instruments, Keck, VLT, Subaru, several radio interferometers, and a couple of space observatories, were to simultaneously observe Atlas during a strictly synchronized window, and not just observe, but conduct the most aggressive observational metrics possible: broad, overlapping ranges, high acquisition rates, and deep exposures. The idea was to create such a density of dimensions that the system, if it is truly multi-configurational, would be forced to choose one macrostate that is consistent across all frames. When I first read the technical description of the experiment, I had a strange feeling that humanity had focused all its attention on a single point, literally pinning a piece of reality in a corner and forcing it to admit who it was. Not a very noble motivation, if you think about it. Day X turned out to be surprisingly calm. No solar flares, no storms over Hawaii or Chile. Even space weather was on our side. Synchronization seconds between observatories were practiced better than military maneuvers. Internal chats were buzzing, but not a word leaked out. Officially, it was just another coordinated interstellar comet observation campaign. At the moment of liftoff, when the short lock command came over the secure channel, I caught myself holding my breath. Silly, of course. The atmosphere, the vacuum, the light, the electronics clicking, all regardless of the breathing of some astrophysicist in a distant office. But the human body is sometimes more honest than the mind. For the first few minutes, everything went perfectly. Data streams flowed, graphs came to life, Atlas appeared in the frame, one after another, in optical, in infrared, in millimeter wave. We waited to see how the three diverging versions would begin to converge, how the error clouds would finally overlap, but the opposite happened. Instead of convergence, we saw a failure. At the intersection of synchronized timestamps at all observatories, I emphasize all of them, narrow, razor-thin time gaps appeared where data was simply absent. Not noise, not a dip in brightness, not detector saturation, but blank holes in the record. It was as if, for a split second, the world stopped reflecting anything in the direction of our instruments. The software, of course, assumed it was a glitch. Buffer overruns, overflows, whatever. But when we pulled out these holes and superimposed them, it became clear they were aligned in time to form a single, perfect step, accurate to within microseconds between continents. The world, synchronously Morganal. And then, right after that blink, something else happened. Once the data was normalized and run through the same aggregator, which plotted three-dimensional trajectories along different observation lines, the error clouds ceased to be three separate bubbles. Now there were four of them, another, fourth, thinnest, strangest ellipsoid appeared, one that didn't match any of the previous configurations. It lay between them, but wasn't a simple middle ground. It played with its own parameters, as if the experiment hadn't forced Atlas to choose one version, but rather added another layer to the branching. It was difficult to draw any conclusions from this. The easiest way was to chalk it all up to a glitch, but somewhere deep down, we all understood. At that moment, when all our eyes were fixed on a single point in space, we hadn't a focused reality. We had merely shown it how diverse our frames were, and given the system an additional degree of freedom. After this, a new ban was quietly introduced at NASA. Officially, it was a restriction on globally synchronous observing campaigns with full range overlap. In layman's terms, this meant never again try to simultaneously look in the same place and so deeply. We returned to a more modest regime, Keck watching its night, VLT its own, Subaru its own. The system again smeared Atlas across three close orbits, the fourth frame living somewhere on the edge of sensitivity, flashing here and there in the statistics, a reminder of the failed attempt to force the universe to decide. Sometimes, leafing through the reports, I caught myself thinking we were going through a strange evolution. At first, we feared Atlas was a hidden ship, a probe, a message. Then we feared it was a trigger for rewriting the sky, a handle in someone's hands. Now, the most frightening thing seemed something else, that it was merely an indicator, a marker, a small test object on which some deeper structure was testing the boundaries of what was acceptable within our frames of reality. In this picture, we weren't even participants in the experiment, but a side effect. And yet, despite the fear and helplessness, I kept coming back to the same internal conclusion. We saw something we shouldn't have seen with this level of technology. We looked further behind the scenes than we were supposed to, but it's already happened. It's impossible to unsee the triple, then quadruple configuration of a celestial body that, according to all textbooks, should have behaved like a boring icy rock. It's impossible to forget that synchronized morgue of the universe, recorded by 100 eyes at once. One can only learn to live with this knowledge. Sometimes, when you look too closely at the same tiny speck of space, the problem isn't that you'll see too much. The problem is that that speck itself will suddenly realize how different you can be, and will begin responding to you simultaneously in all the versions of reality you have access to. Atlas will fly away, the data will become obsolete, official articles will carefully trim the rough edges. But in work folders, in informal notes, in notes in the margins, there will still remain one and the same, very simple, almost childish question that haunts me to this day. If one small interstellar object can behave so differently to three telescopes, what happens to the rest of the universe while we look at it through a single human frame and honestly believe that we see the only reality? For a while after that experiment, life attempted to return to a normal trajectory. Neat articles were published about the chemical composition of the coma, the green glow of diatomic carbon, and the dynamics of the tail. Press releases cautiously repeated, Atlas poses no threat to Earth. The orbit is hyperbolic. The object will leave and never return. The news carried the usual mixture of excitement and boredom. Only among the small circle of people who had seen the fourth ellipsoid did the word hyperbolic no longer sound reassuring. It began to denote not an abstract curve from a textbook, but something like a door slightly open to the side where our usual categories ceased to apply. The strangest response came not from space, but from the ground. A couple of weeks after the blink, I received an email from a colleague at the quantum optics lab, whom I'd previously only encountered at corporate coffee conferences. The subject line was ridiculously simple: phase alignment incident. Inside was a short description of an experiment with a fiber optic interferometer, which they were running at night in test mode. Everything was going perfectly until they decided, for fun, to introduce real 3i/ATLAS ephemerids into the control software as an external modulating parameter. At first, it was a pure trick, to tie the phase shift in one arm of the interferometer to the position of an interstellar comet in the sky. There was no physical connection, just a decorative feature in the GUI, a way to entertain the students and remind them that there was something above their heads other than the lab ceiling. But as soon as they turned on this cosmic harness, the phase began to behave strangely. No noise, no drift. It stuck to the values calculated to correspond to the 4 configurations we'd seen in the celestial data. At times, the interferometer behaved as if it were trying to decide which Atlas branch to synchronize to. The readings bounced, but not chaotically, between 4 clusters that were painfully familiar to me. Naturally, they initially considered local causes: temperature drift, micro-vibrations, electromagnetic interference, but the effect disappeared as soon as the Comet Ephemeris module was turned off. It returned when turned on again. At some point, someone suggested shutting down the internet for the entire floor to make sure it wasn't a dirty trick by a remote administrator. The result was the same: a self-contained interferometer, an autonomous generator, an offline network, and a phase locked in the same 4 states as in our celestial models. I sat over their graphs at night in a dimly lit office and caught myself with an unpleasant thought. Perhaps we ourselves had connected the lab toy to that multi-configuration thing up there. We had given the system the ability to see us through an additional channel. Before, everything had been limited to photons reflected from the comet. Now we had linked the internal degree of freedom of our device to its position, and we got an immediate response. This story never made it into any official report. At the morning call, it was dismissed as insufficiently reproducible, thus creating a convenient excuse to forget. But in the private chat room where such anomalies flocked, it was lumped together with several other oddities. Sporadic glitches in the atomic clock synchronized to signals passing near the presumed position of Atlas. Small but persistent drifts during the radio interferometric observation phase, when the baseline accidentally caught the comet's region along its extension. All of this could be interpreted in the old way, within the familiar paradigm: poorly calibrated instruments, unaccounted for environmental effects, statistical tales. This is precisely the approach that survives in science. Cautious, distrustful, with strict filters for anything that smacks of mysticism. But somewhere beneath the surface, another narrative was taking shape. Atlas doesn't just exist in several configurations, it reacts to the very fact of our decision to measure it. One night, after yet another sleepless shift, I found myself opening old archives, unrelated to comets, ALMA, or JWST, 10-year-old data from laser gravity detectors, calibrated pulsar signals, even noise from magnetotelluric stations. And I was looking for something I shouldn't be looking for. Weak, intermittent correlations with the trajectory of an object that wasn't yet on our maps. I found nothing convincing, and that was perhaps the only thing that reassured me at the time. If Atlas is rewriting reality, as the most pessimistic wing suspected, it's doing so very locally, carefully, like a surgeon, not a bulldozer. Sometimes people ask me if I regret getting involved in this story at all. The honest answer is no. What's frightening isn't that we've seen a multi-configurational object that stubbornly refuses to collapse into a single trajectory in our equations. What's frightening is that we may have encountered, for the first time, a mirror reflecting not the structure of the cosmos, but the structure of our way of looking at it. Atlas, Keck, the VLT, the Subaru, the interferometer in the basement, these aren't a collection of disparate episodes. They are a single experiment in which the universe has carefully returned our own question to us, only in an expanded form. "You want to know where I am?" she asks, as if through a green interstellar comet spreading across 4 orbits. Fine, but then first figure out where you actually are. The irony is that the real ending to this story began not with a new telescope or yet another anomalous data point, but with a very human thing: a leak. Not romantic, not heroic, but rather drearily prosaic. Someone issued an internal report, not quite understanding what exactly they were leaking. The document didn't mention multi-configurational phase states, only cautious wording about inconsistency in the 3i/ATLAS, track between independent observatories, and an unacceptable level of systematic discrepancies. But along with the text, one image was leaked. the one with the 3 error clouds circling the calculated trajectory without touching one another, and a small, barely noticeable 4th ellipsoid, which we hadn't yet dared to show even to colleagues outside our inner circle. The image went to a private forum, from there to an astrophotography chat, and then to a couple of conspiracy theories. By the next morning, someone had already turned it into a meme. Atlas in 4K added the caption DLC to the 4th configuration and spread it around social media. The joke took on a life of its own, but between the laughter, questions began to slip out that I didn't like to hear even in my own head. If your 3 independent measurements don't agree, are you sure the problem is with the object? If the sky map itself starts to diverge slightly in different instruments, are you sure you even have the same map? Usually this point can be dismissed. The general public quickly switches gears. But this time, someone thought to compare our multi-configuration frame with another fragment that had already surfaced earlier. Those same edited Hubble archives, where the green Atlas halo was somehow present from 20 years ago. For the first time, I saw 2 independent leaked artifacts begin to coalesce into a single narrative. And this narrative was not being born at JPL, not at NASA, not at ESO. It was being written by the anonymous internet, overlaying our neat models with crude but in some ways frighteningly accurate metaphors. They're rewriting the past to fit what's arriving now. The comet is a branching marker. Atlas isn't an object, it's a cursor in a reality editor. I could go on and on about how physically incorrect this was. I could point out the equations, the errors, the uncertainties, the limits of applicability. But somewhere inside, a strange coincidence tugged at my nerves. Our own terms, catalog overriding, frame shift, phase configuration, sounded not so far removed from what the people with pixelated planet avatars were writing. And, as often happens, the next step wasn't taken by a theorist or the institute director, but by an operator, a night worker, tired, with 2 shifts in a row and access to the very consoles we'd sworn never to use again to launch globally synchronized observations. In the logs I saw later, it looked almost innocent. A short command line, limited in range, without enabling all spectra, just a test run. Synchronized several ground-based telescopes and one space telescope at one point in the 3i/ATLAS trajectory. Not at the comet itself, but at an empty patch of sky where, according to our models, one of its alternative configurations should emerge in a few days. He wanted to test a simple thing. If we look not where the object is, but where it should be in another branch, will we see anything? A simple, honest scientific question. The universe decided to answer it in its own way. During the first short exposure, nothing special happened. Just noise, a scattering of background stars, and faint traces of satellite tracks. But as soon as the acquisition time was increased and cross-correlation with the radio band was enabled, a faint but persistent pattern emerged in the data. Not an object, not a dot, not a tail. Net. In the composite frame, composed of many minutes, the background noise was permeated with a subtle, almost invisible rectangular pattern as if someone had covered a section of the sky with a translucent grid of coordinates. Each cell contained the same stars, the same noise, but their statistics differed slightly from those of neighboring cells, as if each square belonged to its own version of the same frame. For years, we've been teaching our students that there's no absolute pixel grid in space. It's simply an artifact of our instruments. This time, the feeling was the opposite. The instrument frankly showed that the very fabric of the observed region seemed to be cut into mismatched fragments. When a randomly synchronized data packet from ALMA was added to this, things got worse. In the millimeter range, where stars are barely visible, the same region appeared empty. But when the same artificial grid was superimposed, the cells began to noise unevenly, producing micro-peaks in places where, based on celestial mechanics, another hypothetical Atlas trajectory could have been plotted. For the first time, we began to sense that the comet doesn't simply exist in multiple configurations. It carries with it a coordinate system in which all of these configurations are simultaneously valid. And our attempts to force it to choose a single branch seem as naive as trying to force a monitor to display only one color, when you already have the full color palette enabled. In the management report, we described it much more simply. Structured noise correlations were identified in the region associated with the expansion of the 3i/ATLAS multi-orbit model. Not a word about the grid. Not a word about the feeling that for the first time you see reality showing you not an object, but a marking on which someone is perhaps drawing trajectories. I often think about that operator. He wasn't punished. Technically, he didn't violate protocol. His test wasn't a global campaign. Everything was within the permissible workload. But after that experiment, another line was added to our unspoken rulebook. Not written down in any official document. Don't try to look where an object should be in another version of events. We no longer tested hypothetical extensions of the hyperbola, We didn't adjust the grid to accommodate invisible configurations. We limited ourselves to a modest, almost old-fashioned approach, measuring what the photon produces right now without philosophical exercises. By this point, Atlas had already begun to move away. Its green glow was fading, its activity was declining, and its millimeter wave gas jets were becoming increasingly weak. For most people, this story ended right there. A rare interstellar visitor had passed by, provided a couple of beautiful images, refined a model or two, and then vanished into the darkness. But for those who saw the grid, the four-dimensional ellipsoid, and the synchronous blinking of the sky, nothing ended. Sometimes at night, when I go out onto the roof and simply look at the stars without a telescope, I catch myself with a strange sensation. It's as if somewhere beyond the visible, at the level of what we still call noise, there are movements, rotations, and adjustments that our eyes and instruments are too crude to discern. Not because they're small, because they occur simultaneously in all those versions of the worldview that we can't even record on a hard drive yet. Atlas will move beyond our catalogs. ALMA will switch to other targets. JWST will look at galaxies at redshifts of 10 and higher. But in the code of some calibration scripts, there will still be commented out lines written by tired operators at 3 o'clock in the morning. Jash Geringhun. Do not sync all arrays. Here, phase lock to Atlas disabled. Little human incantations we use to curb our curiosity when we realize we've gone half a pixel further than was safe. And perhaps, decades from now, when another interstellar object enters our system and someone again raises old archives, compares maps, matches coordinates, they will stumble upon these strange fragments of logs, the fourth ellipsoid, the grid in the noise, and they will understand that the 3I/ATLAS story was not about a comet. It was about how one little green dot in the sky made us seriously ask ourselves for the first time, but are we sure that the version of the universe that we are accustomed to considering the only one is really the one that it chose and not the one that is simply more convenient for our software to process?